Welcome back, ladies and gentlemen, to my course on linear algebra in 2D. It's been quite a while since I did my last video, but now I'm back and I am going to tell you in chapter 6 of this course about the Iwasawa decomposition, which is a very beautiful theorem on the geometric structure of matrices or linear transformations. So in essence, we will learn that every matrix or linear transformation can be viewed as a composition of three particular types of geometric transformations, which we have gotten to know already in the previous chapters. So, what we will do today is we will first recall geometric transformations and then in particular study some properties of the orthogonal transformations and the upper triangular matrices, which are the essential classes of transformations we will be studying. And then I will prove the Iwasawa decomposition, the existence of this matrix decompositions into matrices, into geometric transformations of a certain type. Now, we already encountered four types of linear maps in chapter 2, the rotations, reflections, shearings, and scalings. And we will see here that these are actually the basic building blocks for all invertible geometric transformations of the plane. So any invertible linear map essentially is a composition of these types. Now, let us quickly recall what these types actually are. A rotation, which we called phi alpha by an angle alpha, is given by a rotation matrix of this form. So we have this matrix R alpha with the cosine and sine entries in this particular pattern here, and multiplied with any vector x, what it does is it rotates this vector x by the angle alpha counterclockwise. A reflection across some given axis, some line in the plane, reflects vector x along the perpendicular line to this axis. So, for example, if we take the E1 axis, just the first coordinate axis here, as our reflection axis, then what it does, it takes a vector x and just mirrors it to the other side of this line. So in this case, it just flips the second coordinate of our vector to the negative of it, while the first coordinate is preserved. And this reflection here is achieved by this simple matrix S1, which you can easily verify. If you multiply any vector by this matrix, then the first coordinate stays the same, and the second coordinate gets sign flipped. We also learned that if you want to reflect across an arbitrary axis, L, which lies at an angle alpha with respect to the first coordinate axis, what you can do to obtain the reflection matrix for this reflection across the line L, you basically rotate the line L onto the first coordinate axis, then you use this reflection here, represented by this matrix, and then you rotate it back onto the line L, and if you combine these operations, then you get the matrix that represents the reflection across the line L. And you can always write it in this particular form here, where alpha is the angle enclosed by L and the first coordinate axis. Then we also learned about scalings, also called dilations. And these are maps that stretch or shrink the distances along two axes by given positive factors lambda 1 and lambda 2. And for our purposes, it's enough to consider the scalings along the two canonical coordinate axes, so the E1 axis and the E2 axis. And we call these standard scalings. So a scaling, such a standard scaling, is given by a matrix D for diagonal of this form here. So it's a diagonal matrix because the only non-zero entries are the two diagonal entries and the lambda 1, lambda 2, so these two scaling factors. And here in this example, we have lambda 1 equal to 1/2, so we actually shrink the proportions along the E1 axis, and we have lambda 2 equal to 2, so we stretch the proportions along the E2 axis. And you can see if we have this house here given originally, then the scaled version of it gives you this red house here where the height has been doubled but the width has been halved by applying this matrix here with lambda equal to 1/2 and lambda 2 equal to 2. Then we had the so-called shearings, which is maybe a bit more complicated to explain. So what a shearing does, it has a given line L and it translates all points x in the plane parallelly to this given axis L. And the distance by which it translates these points is proportional to the distance of the point to the line L. The simplest case here is if the shearing is happening parallel to the E1 axis. So in this case, the shearing is given by this matrix N here, which is just 1, 0 in the first column and A1 in the second column. And A is the proportionality factor for this translation. And these will be called standard shearings. And here we have an image. What happens with this box here, when it gets sheared, it becomes a parallelogram. And you can see all the points that are not on the E1 axis are translated a certain distance parallel to the E1 axis. So, for example, the points on the E2 axis, they all get translated onto this line here. And it's clear that the higher up they are on the E2 axis, so the larger the distance to the E1 axis is, the further they get translated by this shearing. So in effect, if x is a vector with coordinate x1, x2, then what happens is the x2 coordinate stays the same, hence translation parallel to the E1 axis, and the first coordinate x1 gets translated by some amount that is proportional to the x2 coordinate. Now let's take a closer look at so-called orthogonal transformations. And for these, recall from the first chapter of this course that the norm, or the length of a vector x with coordinates x1, x2, is simply given by the square root of x1 squared plus x2 squared. So if you recall Pythagoras' theorem, then it makes sense to have this formula here defining the length of a vector. Now, an orthogonal transformation, phi, is a linear transformation that preserves the length of a vector in the plane. So it satisfies by definition the property that the norm of phi of x equals the norm of x for any vector x in the plane. And they are called orthogonal transformations because their columns, or also their rows, in the matrix representing them are mutually perpendicular to each other, but this is not something I will pursue any further here, so you can try to prove this if you like or look it up, but I just state it here to explain where the name orthogonal comes from. Now, we can see that both rotations and reflections are orthogonal transformations, and we can do this by a direct computation. So we have a rotation r by the angle alpha and apply this to some vector x, and then we look at the norm of the resulting vector. So r alpha times x, if we write it out in coordinates, is this. Here we have the rotation matrix times the vector x. If we multiply this out, now note the colors, we get cosine alpha times x1 minus sine alpha x2 in the first coordinate. In the second coordinate we get sine alpha x1 plus cosine alpha x2. And now we just apply the formula for the norm of this resulting vector here, which is first coordinate squared plus second coordinate squared, and we take the square root of it. And now if we expand these two terms in the squares here, we see that a few parts cancel out. So from the first bit we get cosine alpha squared x1 squared minus this bit here, 2 times cosine times sine of alpha times x1 x2 plus sine alpha squared x2 squared plus, now we expand this part, sine alpha squared x1 squared plus, and now the same bit as we had here, but with a positive sign, 2 cosine alpha sine alpha x1 x2 plus cosine alpha squared x2 squared. So as I said, these parts here cancel out, and we can reorder the terms a little bit. So we have the factors for x1 squared and x2 squared. So we get cosine alpha plus sine alpha squared as sum times x1 squared, and for x2 squared we get sine alpha squared plus cosine alpha squared. And if we remember our trigonometry from school, then we see this, and equivalently this here, is just the number 1. So this expression here equals x1 squared plus x2 squared, and the square root taken of it, which by definition is identical to the norm of x. So indeed we see by direct computation that a rotation applied to a vector x has the same length, the same norm as the original vector had. Hence rotations are orthogonal. And you can use a similar computation to verify that also reflections are orthogonal. So we apply the reflection matrix to the vector x, and then we can expand all the terms to a similar computation, and we find that also the length of the reflected vector is identical to the original vector, which is of course a quite intuitive result if you think about it. But here we can show it, and if you want, you can make this computation explicit as an exercise. It's very similar to the one here. One consequence of this is that since both rotations and reflections are orthogonal, it follows that any product made up of these two types of transformations is also an orthogonal transformation. So if T1 to Tk are all either a rotation or a reflection, and we have a product of k of such maps or matrices, and we apply this to a vector x and look at the norm, then, well, inductively we can do the following. Since T1 is orthogonal, this is the same as T2 times T3, Tk times x. Now we can say since T2 is orthogonal, this is the same as the norm of T3 times Tk times x, and so on, until we find it's the same as the norm of Tk times x, which, because Tk is also orthogonal, is the same as the norm of x. And we can even prove that every orthogonal transformation is a product of a rotation and a reflection, but we will not do this here. But this would essentially show that rotations and reflections not only are orthogonal, but in fact make up or generate all orthogonal transformations. And what we have seen here, that products of orthogonal transformations are also orthogonal. We could expand this into the theorem that orthogonal transformations make up a structure called a group. So the set of all orthogonal transformations forms a group, since inverses are also orthogonal, and the identity map is an orthogonal map. But I do not want to pursue this here, because I would like to study groups in much more detail in a different course on this channel. So I'm not going into it here, but I just mention it that this insight here is crucial to finding that orthogonal transformations form a group. Now let's study the so-called upper triangular matrices, which is, if you want, a type of geometric transformations that's complementary to the orthogonal ones, and we will see in a few moments what exactly I mean by that. Now, an upper triangular matrix is a matrix of this form here. The matrix A has only non-zero entries or possible non-zero entries on the diagonal and above the diagonal. So the one entry below the diagonal is 0. And because this has kind of a triangular shape, we call them upper triangular. Consequently, a lower triangular matrix would be one which has a 0 here and arbitrary entries in these 3, but we don't care about these here. Now, an upper triangular matrix of this form is invertible if and only if x and z are different from 0. That's something you can very easily check using what we've learned so far about invertible matrices and how to determine if a matrix is invertible. And we observe also that the product of a standard scaling D, so a diagonal matrix D, and a standard shearing N is an invertible upper triangular matrix. We just do the computation to see that. So the standard scaling is a matrix of this form with diagonal entries lambda and mu. And the standard shearing is in fact a special type of upper triangular matrix, a so-called strict upper triangular matrix, because it has only ones on the diagonal and some possible non-zero entry above the diagonal. And if you multiply these two, you get a matrix of this shape here. The diagonal entries stay the same, and as the upper entry you obtain lambda times a plus mu. And with the entry x here being lambda strictly greater than 0 because it's a standard scaling, and similarly mu being equal to this entry z then strictly greater than 0, and y obviously is then this entry here. Now the product of two upper triangular matrices, A1, A2, is again an upper triangular matrix, which you can also verify by directly multiplying two of these upper triangular matrices. And if A is an invertible upper triangular matrix, then the inverse A to the minus 1 is also upper triangular, which you can verify directly if A is this upper triangular matrix and x and z are non-zero. Then you can write down this matrix here, and just by using the multiplication formula here you can simply verify that this matrix is in fact the inverse of this one. And again, we could use this to prove that the upper triangular matrices also form a group, but again, I do not want to pursue this any further here and leave this to a different course. Now, if we have a matrix that is both orthogonal and upper triangular, then it has to be the identity matrix. So this is what I meant when I said that orthogonal transformations and upper triangular matrices are complementary to one another. So you can't have something that is both unless it's the identity matrix. More precisely, consider lemma 1 here. If K is an orthogonal matrix, A is a standard scaling, and N a standard shearing, then if K is in fact equal to the product AN, then K has to be the identity matrix. Let's prove this. So we know from what we just saw on the previous slide, that AN is upper triangular. So AN is some matrix of this form here with positive diagonal entries, because we assumed A to be a standard scaling and their diagonal entries are positive. And now we see what this transformation does if we apply it to certain vectors. And since we assume that AN is equal to an orthogonal matrix K, so that this matrix here is also orthogonal, it means that the norm of AN times X equals the norm of X for all vectors X. And now let's see where this leads us if we apply it to certain vectors. So for example, we take E1, the first canonical basis vector, multiplied by this matrix here. Then take the norm. So the norm of this is just the norm of the first column of AN, so the norm of the vector lambda 0. And we know, because AN is supposed to be orthogonal, that the norm of this has to be identical to the norm of the first canonical basis vector, because we plug this in here. And the norm of this one is of course 1. So this implies that lambda has to be equal to 1. And well, just from this equation, it could also be lambda equal to -1, but we can exclude that because we know that lambda is positive. Because, again, A is a standard scaling, so lambda is positive. We can't get -1 as a solution here, so we get lambda equal to 1. So already we know this one, this entry has to be 1 if this matrix is orthogonal. Now let's apply this matrix to a different vector, namely the second canonical basis vector. This gives us then the second column of the matrix with entries A mu. And if we take the norm, then again by the assumed orthogonality, we know that the norm of this has to be equal to the norm of the second canonical basis vector, so it's also equal to 1. And we can write this out. So 1 is equal to square root of a square plus mu square. And if we solve this for mu, then we find that mu is equal to the square root of 1 minus a square. Again, we can discard the possible negative solution because we know that mu is positive from the standard scaling. And we apply AN to a third vector, namely the vector 1, 1. And what we get is the vector 1 plus a square root 1 minus a square. So we already plugged in the values for lambda that we found here, lambda equal to 1, and the value for mu that we found here. And if we multiply this matrix then by 1, 1, we get this vector here. We know by the assumed orthogonality that its norm has to be equal to the norm of the vector 1, 1, which we can easily compute to be the square root of 2. So let's write this out. If we ignore the square root, so we just square the equation on both sides, we get 2 equal to 1 plus a square plus 1 minus a square. And yeah, we can simplify this to 2 equal to 2 times a plus 1. And of course, this can only be true if a is equal to 0. And a being equal to 0, if we revisit this one, means, of course, then that mu is equal to 1. So what we have found is that indeed this matrix here has to be the identity matrix. Okay, we found that lambda is equal to 1. Then we found that a is equal to 0. And this implied then that mu here is equal to 1. So we have 1, 1 on the diagonal and 0 above and below the diagonal. So it's the identity matrix. And this is what we wanted to prove, that if an upper triangular matrix coincides with an orthogonal matrix, it can only be the identity matrix. Now keep this lemma in mind. We will use it later when we prove the Iwasawa decomposition, or rather the uniqueness of the Iwasawa decomposition. And what this Iwasawa decomposition is, we are going to see now. Here we have theorem 2, the statement of the Iwasawa decomposition, which is due to the Japanese mathematician Kenkichi Iwasawa from 1949. He did prove it in a more general context. I just rephrase it here for the particular case of 2x2 matrices, which is probably a bit easier to understand than the original theorem. And it says that any invertible 2x2 matrix T can be written in a unique way as a matrix product T equal to K times A times N, where K is an orthogonal matrix, so a product of a rotation and a reflection matrix. A is a standard scaling matrix, and N is a standard shearing matrix. Okay, so this theorem tells us that any invertible linear map is a composition of a rotation or reflection, a scaling, and a shearing. And that is a very interesting geometric interpretation of linear maps. Now, you could ask, so okay, if T is already an orthogonal matrix or an upper triangular matrix or a scaling or something, what would it look like here? Well, of course, these factors can be trivial. They can be the identity matrix. So for example, if T is already a rotation, then we would simply have the case that A and N are the identity matrix. So this would be consistent with this decomposition here. We want to prove this theorem, and I just quickly want to walk you through the idea of the proof, the strategy that I'm going to follow. So what we want to show is that T is a product K times A times N. And we will use that if T is invertible, then each of these matrices K, A, N have to be invertible as well. Now, the idea to prove this is to construct the inverse of T by geometrically undoing the effects that these individual transformations here have. So we undo the effect of the transformation T, but step by step. So by undoing each of these transformations that are supposed to make up T. So what we want to have is we want to find an orthogonal matrix K0, a scaling matrix A0, and a shearing matrix N0, so that we apply K0 to T, then apply A0 to the product of K0 and T, and then apply N0 to the product of A0, K0, and T, that we get the identity matrix. So if we step by step apply K0, A0, and N0 to the transformation T, then we undo the geometric effect that T has, and we end up with doing nothing with the identity matrix. What this implies is that the product N0, A0, K0 must be the inverse of T. Okay, if we have this equation here, then this part here must be the inverse matrix of T. And yeah, then we can simply invert this again, and we find that the matrix T is simply the product of K equal to K0 inverse, A equal to A0 inverse, and N equal to N0 inverse. And in this way we will find the three factors K, A, N of the Iwasawa decomposition. Okay, I hope that makes it clear. And now we will go about finding K, A, and N. We begin with K, with the orthogonal part, and make the following consideration. So we have the matrix T, and we know from our previous chapters that a linear map or a matrix is uniquely defined by the images on two basis vectors. So for example, if we take the two canonical basis vectors, E1 and E2, and we have the images v1 of e1 and v2 of e2. Then we know T, our matrix T, is uniquely defined by these two images here. Now, if we look at E1 and its image V1 under T, under the action of the matrix T, then we have an angle alpha here between these two vectors. And we can think of it as rotating the axis E1 by an angle alpha to get the axis through the image vector V1. And to undo this, we apply a rotation R0 by the angle minus alpha to rotate V1 back onto the axis of the E1 vector. Okay, so that would be this rotation here. It takes V1, rotates it onto a vector V1 prime that lies on the same axis as the E1, the first canonical basis vector. And yeah, it does something with the vector v2, so the image of e2, we don't care about this right now, but of course it also gets rotated to some vector v2 prime. Okay, so by applying R0, we make sure that we rotate v1 to a vector onto the e1 axis. And now we continue undoing the effect of t by looking at the vectors v1 prime and v2 prime. If v2 prime lies below the e1 axis, as is the case in our example here, then we apply a reflection S0 across the e1 axis. And this one maps v2 to a vector v2 prime to a vector v2 prime prime, which lies above the e1 axis. And our vector v1 prime is not changed by this because it lies on the e1 axis, so it's not affected by the reflection. So v1 prime prime is identical to v1 prime. Both the rotation R0 and the reflection S0 are orthogonal matrices, as we've seen in the beginning of the video. And so we can combine them into one orthogonal matrix K0. Okay, the product S0 times R0, so first applying R0, then applying S0, gives an orthogonal matrix K0. And this K0 performs the map of the vector v1, the original image of e1 under the map T, to v1 prime prime, and the map of v2 to v2 prime prime. Okay, so we've taken the two images, v1, v2, of the two canonical basis vector under the map T, and by applying this orthogonal matrix to it, we get these vectors v1 prime prime and v2 prime prime. And of course, if we had the situation that v2 prime had been above the e1 axis, then we would simply have chosen the identity matrix for this reflection here. So in that case, K0 would be a pure rotation. Okay, now we have found our orthogonal part to undo the effect of T, and we will continue with v1 prime prime and v2 prime prime to further undo the geometric effects of our original transformation T. So by construction now, v122 lies on the e1 axis, and this means it is a multiple of the first canonical basis vector e1, say by a factor of lambda. And also we say that mu is the e2 coordinate of v2 prime prime. Okay, so v1 prime prime is lambda times e1, and v2 prime prime should have the coordinate, the component of length mu along the E2 axis. Now we choose a standard scaling A0 with diagonal entries lambda inverse and mu inverse that dilates the E1 axis by the factor lambda inverse and the E2 axis by the factor mu inverse. What this achieves is that V1 prime prime is mapped to E1. Okay, because we scale V1 prime prime in exactly the right way so that this scaling here transforms it onto E1. And what it also achieves is that the scaling A0 maps V2 prime prime to some vector V2 prime 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 whose E2 coordinate equals 1. Because before the E2 coordinate was mu, then we multiply it by mu inverse and it therefore becomes 1. Okay, we don't know anything in particular about the E1 coordinate of this vector here, but we know that the E2 coordinate is 1, so it's at the same height as the second canonical basis vector. And now what we want to do, we want to apply a transformation that leaves the V1 prime 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 vector fixed, so that preserves the first canonical basis vector and that moves V2 prime 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 onto the second canonical basis vector. And we can achieve this by applying a standard shearing N0 with entries 1, 0 and minus A1. So this is parallel to the E1 axis, and A is just chosen to be the E1 coordinate of this vector V2 prime prime prime. Okay, so just this little distance here, this is A. And if we shear the plane by minus A, then what happens is that we will undo this translation here, and this will move V2 prime 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 precisely onto E2. And E1 will not be affected by this because it's on the E1 axis, so the shearing leaves every point fixed on this axis here. So what we have constructed now is a sequence of matrices K0, A0, N0, such that if we apply this sequence of matrices to V1, which was the image of the first canonical basis vector under T, then it gets mapped to E1 again. And if we apply the sequence of matrices to V2, so the image of E2 under T, then it gets mapped to E2. So in other words, this sequence of matrices composed with T applied to E1 or applied to E2 fixes these two basis vectors. But this implies that the product N0, A0, K0, T has to be the identity matrix, because the identity matrix is uniquely determined by the property that it maps E1 to E1 and E2 to E2. And this is just another way of saying that the product N0, A0, K0 is equal to the inverse of our original matrix T. So we have found our desired Iwasawa decomposition. It is simply given by T equal to Kan, where Kan are just the inverses of K0, A0 and N0 respectively. And yeah, you can verify immediately if you multiply this by this, then the K0 and K cancel out, the A0 and A cancel out, and the N0 and N finally cancel out, and we get the identity. Now, this concludes the proof of the existence of the Iwasawa decomposition. And what remains to prove is that these factors here are actually unique for the given matrix T. This is a bit more technical, less geometrical than the existence proof. So let's assume we have another decomposition of T, which is of this Iwasawa kind, so say K prime, A prime, N prime. And our goal will be to show that then these have to be identical factor-wise. So if we're given an equation like this, then it is equivalent to an equal to k inverse times k prime times a prime times n prime. We can simply multiply on the left by k inverse, move it over here. And because this is a product of two orthogonal matrices, the product is again an orthogonal matrix, so we can summarize this for short in a matrix K tilde. Now, A and A prime are standard scalings, N and N prime are standard shearings, so we can write the left-hand side as the product of a scaling and a shearing, so an upper triangular matrix, lambda mu A for certain suitable values lambda mu and A. And the right-hand side, here we have A prime N prime, so an upper triangular matrix. Here lambda prime mu prime A prime with suitable values, but multiplied on the left by this orthogonal matrix K tilde. Now, what we can do is equivalently write this as an upper triangular matrix equal to K tilde, because we can just multiply by the inverse of this matrix here, move it to the left-hand side of the equation. So we have this times the inverse of this one. And now recall from what we know about the upper triangular matrices, the inverse of an upper triangular matrix is also upper triangular, and the product of two upper triangular matrices is upper triangular. So this whole product here is again an upper triangular matrix with suitable values lambda tilde, A tilde, mu tilde, whatever they are, we don't care, but we know it has this form and this entry must be 0. And this is equal to the orthogonal matrix K tilde. And now recall our lemma from before. Lemma 1 showed us that if we have the situation that an upper triangular matrix is equal to an orthogonal matrix, then it has to be the identity matrix. There's no other possibility. Okay, so K tilde is actually the identity matrix, but since K tilde was defined to be K inverse times K prime, it follows that, that K prime is equal to K. Because if this is the identity matrix, we can just multiply by K on both sides and then we get this equality. Okay, so we found already that K and K prime are identical. But it also follows then that AN and A prime N prime are identical. Why is that? That simply follows from this equation here, because we found that K tilde is the identity, so we can leave this out here. So then we get immediately AN equal to A prime N prime. And then just by comparing coefficients, we find that lambda equal lambda prime, mu equal mu prime, and A equal A prime. And the lambdas are the orthogonal, the diagonal entries of A and A prime respectively. So we immediately find that A equals A prime. And then we can cancel out A on both sides and we directly find that N also equals N prime. So this concludes the proof of the uniqueness of the Iwasawa decomposition, because what we have shown is that if we assume we have two decompositions of one and the same matrix T, then it follows that each corresponding factor on the left must be identical to the corresponding factor on the right. So this decomposition is really unique for the given matrix T. And this concludes the proof of theorem 2 of the statement for the Iwasawa decomposition in total. Now, let's look at an example. Here we have this matrix with some rather nasty entries, but of course I constructed it so that's actually rather easy to compute. Let's have a look. So we have the first column square root 3 divided by 2 and 1/2. And in the second column we have 3 times square root 3 minus 2, and all of that divided by 2. And the second entry being 2 times square root 3 plus 3, all of that divided by 2. This is our matrix, and we want to compute the Iwasawa decomposition. Now the first step is to find the orthogonal part. So recall from the proof of the Iwasawa decomposition, what we can do is we can rotate the image of the first canonical basis vector E1, so TE1, back onto the E1 axis. And this is the rotational part that we want to have. Okay, what we do, we first compute what this image actually is. So we just take the first column of T, because that's T times E1. And if we compute the norm of this vector, then we find that conveniently it has norm 1. So that makes life a little bit easier. And what we do with this, we draw a little sketch. So here's our first canonical basis vector E1, and here's T1, TE1, the image of E1 under the map T, which has been rotated by some angle alpha with respect to the original E1. And now we know that the first entry, the E1 coordinate of TE1 is square root of 3 divided by 2. So we just found that here. So the length of TE1 in the E1 direction here, this is just square root of 3 divided by 2. But if we look at this sketch here, then we have a right angle here. We have the angle alpha here. We know that the length of this bit here is 1, which we just computed before. So this distance here, square root of 3 divided by 2, is actually the cosine of this angle alpha here. Okay, so we know the cosine for the rotation. And yeah, in this situation, this implies that alpha is the angle pi over 6, or which is the same as 30 degrees. Of course, the same cosine value can appear for different angles, but yeah, from the position of the vectors here relative to each other, it's clear that this has to be the 30-degree angle. So we find that K is in fact a 30-degree or a pi over 6 rotation. So it's this rotation matrix here. And if we evaluate these expressions, then we find that K is the matrix with columns square root 3 by 2, 1 divided by 2, minus 1 divided by 2, square root 3 divided by 2. So we found our orthogonal part, and now let's move on to find the diagonal or the scaling part of our matrix T. How do we do this? Well, we first determine the upper triangular part of T, and we get this by simply multiplying T on the left by the inverse of K. So to get the inverse of K, we simply have to move the minus sign, so the rotation angle alpha gets replaced by minus alpha. And yeah, then we get this matrix T here, and we multiply these. It looks a bit nasty, but what we actually get is a rather nice matrix here. It's the matrix with entries 1, 0 and 3, 2. And this is, as we expected, an upper triangular matrix, and this has to be the product A times N of our Iwasawa decomposition. Now, we can read off the diagonal entries of A directly from this upper triangular matrix here. So A is the matrix with diagonal entries 1, 0, 1, 2, and the off diagonal entries 0. And we know K and A now, so it's easy to determine N from this. So the shearing part is obtained by multiplying T on the left by K inverse and then by A inverse. So This is A inverse, and this is just K inverse times T as before. And what we get is the shearing matrix with diagonal entries 1, of course, as every shearing, and the proportionality factor 3. And this is n. So to sum up, we found that the Iwasawa decomposition of this matrix T, which was given here, is given by these three matrices here: K, the orthogonal matrix, the rotation, the scaling matrix A, and the shearing N. So this concludes our example, how to compute an Iwasawa decomposition of some matrix. So let me make some final remarks at the end. As I stressed before, the Iwasawa decomposition is a very interesting and beautiful result, as it tells us that every invertible linear transformation, no matter how weird or complicated it might look, is in fact a composition of three fundamental types, namely the orthogonal transformations, the scalings, and the shearings, where the orthogonals can themselves be split into rotations and reflections. But it's indeed very nice to know that these three, or four if you like, simple types make up all transformations, or generate all transformations of the plane. And if a theorem gets a name, a big name, from a mathematician that discovered it, then you can imagine it is a very serious and important theorem. And of course, the original Iwasawa decomposition does not only apply to 2x2 matrices, but it can be generalized with a corresponding statement to n×n matrices, or even much more general than that. The original theorem that Iwasawa proved in 1949 already applied to a very general class of continuous transformations on topological spaces. And this decomposition also pops up in applied mathematics. So if you take a course on numerical analysis, you might encounter it without even knowing that you encountered it. And there it is often called the QR decomposition. So where some matrix A is decomposed into a product Q times R, where Q is an orthogonal matrix and R is an upper triangular matrix with positive diagonal entries. And yeah, you see this is exactly analogous to our Iwasawa decomposition. And then, yeah, there are all kind of algorithms to compute this QR decomposition, or to use this QR decomposition to solve some kind of numerical problems. But of course, this is a topic for a different course. Now, I hope you liked this lecture about the beautiful Iwasawa decomposition, and do not forget to like this video and subscribe to my channel if you haven't done so.